Hi everybody, this is going to be our note for 7.2 and 7.3 because Chapter 7 is about exponential functions. So in order to understand exponential functions, we have to do some review on exponents. So 7.2 and 7.3 are kind of just review of exponents, and then we'll get into the actual exponential functions. So let's start at the very beginning. It's a very good place to start. We have to recall that a power is an expression made up of two parts. You have a base, which is like a big number, and then we have the exponent, which is the number above. So our base in this example is 5, and the exponent is 4. Our base in this example is negative 5 in the brackets, and the exponent is 4 here. Our base here is x, and the exponent is 3. Look at this side, we have a base of 7, and yeah, we can have a negative exponent. Here we have negative 5, 4. So our base is going to be 5, and our exponent is going to be 4. Our last one, because it's in the brackets, 3x is the base, and the exponent is 4. Now I'm sure there's some questions. For example, how come this negative 5 has a base negative 5, but this negative 5 does not have a base of negative 5? Well, that actually plays in parts with our brackets. Our brackets are what's containing the number here so that we know the negative is with the 5. In this case, the negative is not part of the 5. Meaning if I were to expand this out here, I'll do that up here. What this is really saying is negative 5, and then we're just doing all these 5s that are positive with each other. We're kind of doing these first. So when I see a negative and there's no brackets here, that means the negative is not part of the base here. The base is still 5, and the negative is just what happens afterwards. So I would do 5 to the power of 4, and then apply the negative afterwards. While in here, this is just negative 5 to the power of 4. So mathematically, a power is the repeated multiplication of the base of an exponent, of the base an exponent number of times. Sorry, that's what the bracket or the quotation marks are there for. So in expanded form, we know that this is 5 times 5 times 5 times 5, and this would be negative 5, negative 5, negative 5, negative 5. And I kind of wish I put a line here just for this top example now, but now we know this one, that if this negative is here and this is not with the brackets like it is down here, I do the 5 to the power of 4 and then apply the negative at the very end. So how do we write a single value or variable as a power? For example, x, and we want it to be like x with a 1 exponent. Well, we just assume that there's an invisible 1 there. So if I don't see an exponent here, we just know it's 1. So those are the kind of basic rules that we learn. We're going to go over these laws of exponents now. Okay, so let's go over these laws of exponents. You already know most of them, but there's some you might just need a refresher on. So I'll try and go quickly through this. So if we're multiplying these exponents with the same base, what are we going to do when multiplying powers with the same base? We add the exponents. And what this means is if we really expanded this out, 4 to the power of 2 is 4 times 4. And then if I multiply that by 4 times 4 times 4 times 4, and that's the last group of 4, this is the first group of 4. How many 4 times 4s are there? That's 4 times 6. So we do a m plus n. For dividing, like we see here, 6 to the power of 6 over 6 to the power of 3. This is the same as saying 6 times 6 times 6 times 6 times 6 times 6 over 6 times 6 times 6. So then if I cancel some of these 6's out, so these cancel, these cancel, these cancel, all I'm left with is 6 to the power of 3, which is really if I just subtract these exponents. So in dividing powers with the same base, subtract the exponents. So a is equal to m minus n. Our next one is power of a power. If I have 3 to the power of 2, and then this is the power of 3, this is like saying 3 to the power of 2, 3 to the power of 2, 3 to the power of 2, which then according to our multiplying rule, I'm going to add the exponents here because I'm multiplying these with the same base, so I'm going to add the exponents, and I end up getting 3 to the power of 6, which if you think about it, is just our power multiplied by another power. So to simplify a power of a power, we're just going to multiply the exponents, which is equal to am times n. All right, these are the two that people might might need a refresher on. So if I have, for the power of a product, if I have an exponent on the outside and I have multiple things on the inside here, what this is really saying is like 2xy, 2xy, oops, 2xy. Because this is the power of 3, so I just did this 3 times. So if I multiply these all together, well, 2 times 2 times 2, that's like 2 to the power of 3. X times x times x. I mean, if there's an exponent of 1 on all of these, I'm going to use my my addition rule here for my exponents. I'm going to add them together. So I'm going to get x to the power of 3, y to the power of 3. So then this 2 to the power of 3 we can simplify, but I just want to show what our rule is here, that if I have a power of a product, we distribute the exponent to each part of the product. So like here it's a times b to the power of m. I can rewrite this as a to the power of m, b to the power of m. So just like over here, it's like I'm getting my exponent and I'm applying it to the first part, second part, and the third part. So the exponent goes to the first one, second one, and the third one. So I get 2 to the power of 3, x to the power of 3, and then y to the power of 3. Our last one is the power of a quotient, which is very similar to the power of a product. It's just I'm going to be, to simplify the power of a quotient, distribute the exponent to each part of the quotient. So it's like we're just applying the exponent to the top number and then also to the bottom number. And our proof for that, to show that, is, well, if I have x over y to the power of 4, that's like saying x over y, x over y, x over y, x over y. So then according again to our addition of our, our multiplication rule here, if these are all 1, because I'm multiplying them, it's going to be x to the power of 4 and y to the power of 4. So it's like I'm just basically multiplying the exponent into the top, or applying it, sorry, to the top and the bottom number. So those are our rules for our laws of exponents. All right, so let's get to some examples. So I'm going to show some of the steps here. You don't have to do them. You can just kind of answer it if you want to, but I'm going to show all the steps because it's our note. So 9 to the power of 2 is like 9 times 9. We get 81. Our next one now has negative 9, but negative 9 is in the brackets. So this is like saying negative 9 times negative 9 is also going to be 81. For C, this is our example we saw on the first page where the base is 9 here and there's just a negative in front of it. So this is really what we're going to do, is we're going to do the 9 times 9 here, and then the negative will apply afterwards. So I get negative 81 here. And this is all because this negative is not in the brackets. So that distinction is very important. For part D, this is going to be what we learned before, the quotient one. Yep, power of a quotient. So I'm going to get 1 to the power of 3, and then 2 to the power of 3, which I would go down, but I don't have a lot of space. I'm going to go sideways. 1 to the power of 3 is 1. 2 to the power of 3 is not 6, not 2 times 3, 2 to the power of 3. 2 times 2 times 2 is going to be 8. For our last one, if we wanted to, we could just show it this way to make it a bit easier for us, like this. And that way I'm going to get 1 over 4. Or we could think of it as, I'll do it up here, I guess, 1 And because we can apply the negative to, because it's inside the brackets, we can just put it with the numerator here. So I'm going to get, same thing, 1 over 4. I could put it with the denominator, but I'm used to putting it with the numerator. So just some quick evaluations. All right, for example 2, we're just going to simplify, which means we're going to write as a single power. We're not going to solve it. So for our first one, I think it's not too bad. I'll zoom in a little bit more. I probably should have done that earlier. I'm very sorry. So because I'm dividing here, I have my division sign. I'm just going to subtract my exponents. So as a single power, this is just negative 3 to the power of 2. Same thing here. I'm just going to subtract the 2. So I'll show the step for this one. We're subtracting the exponents because I'm dividing them. I get 7 to the power of 5. For C, exponent to another exponent, so I'm going to multiply them. Again, you don't have to show the step, but I'm doing it just so you can see. I get that. Okay, our last one. I'm going to treat this, like we do BEDMAS, we put brackets around the top and the bottom of a fraction and solve that first. So I'm going to be adding these exponents. So 15 plus 5 gives me 3 to the power of 20 over 9 to the power of 9. Now there is something tricky we can do here. I don't know, tricky, but we could actually rewrite this 9 as an exponent. And if we did that, we would have the same base as the top here. So like 9 is the same as 3 to the power of 2. And there's an exponent of 9 still here, so that's going to be here. So all I'm doing here is saying that 9 is equal to 3 to the power of 2, and I just substitute that in here. And now, if I wanted to, I could simplify this further. Keep in mind, I haven't done anything at the top at all, just to the bottom part. Now I have exponent to exponent. I could multiply these together. So 3 to the power of 18. And then now I'm dividing them, and I've simplified the top and bottom as much as I could. I'm now just going to do subtraction. I get 3 to the power of 2, which is equal to 9. Now, if you wanted to as well, you could double check this on your calculator, but you should get 9 as your answer. Example 3 says simplify, so we're going to do the same thing. We're going to write this as a single power. So first thing I'm going to do, 3 to the power of 4 here, or x to the power of 3 to the power of 4. I'm going to multiply those, so I get x to the power of 12. And now these two x's are being multiplied together, so I'm going to add the exponents to get x to the power of 14. For B, again, I'm going to do the numerators and denominators separately. The denominator is nothing here, so nothing to simplify there. So here I'm going to follow BEDMAS first, and I'm going to multiply the exponents. So I get x to the power of 8 over x to the power of 7. Then I'm going to do, again, numerators first. We're going to simplify the top. So I'm going to get x to the power of 11 because I'm going to add these together. X to the power of 7. And then we get x is equal to 4 because I'm going to subtract the top and the bottom. So hopefully I don't have to show that step anymore where I'm showing I'm going to add these to get 11. I'm going to subtract these to get x to the power of 4. You can if you need to, but hopefully we can, kind of get through each step without having to do that. All right, example 4, it says rewrite each with a common base or the base indicated. So it's actually very similar to what we did over here, with where we can make a 9 equal 3 to the power of 2. So it says rewrite 64 to the power of 3 as a power with a base of 4. So we want to know it's got to equal 4 to the power of something as our answer. So how could I write 64 to the power of 3 or something with a base of 4? Well, you could just try 4 to the power of 2, 4 to the power of 3, 4 to the power of 4, and see if you get 64. And if you did that, you would find that 4 to the power of 3 is equal to 64. So I'll just put it over here, 4 to the power of 3 equals 64. So all I'm going to do is replace the 64 now with 4 to the power of 3. And then I still have my exponent 3 here, so it's still here. So maybe I'll put brackets around this to show that. So this is the same as this, and the exponent 3 is still here. And now I see an exponent to another exponent, so I'm going to multiply those exponents. So my answer is 4 to the power of 9. as a base of 4. And then as for b, it says rewrite with a common base and simplify. This is kind of like what we saw above, where I can write 9 as 3 squared. So I'm going to get 3 squared squared, and then 3 to the power of 2 here. So now I can use my exponent laws. I can multiply that exponent to another exponent, 3 to the power of 4, 3 to the power of 2, and now I can just add these together to get 3 to the power of 6. Alright, there's your homework, but I'm going to get on to the 7.3 note as well. Alright, here's the 7.3 note, integer exponents. So recall these rules that we just looked at right now. If I'm doing this, I'm going to add these. I'm going to apply the exponent to both of these. Here I'm going to subtract these ones, the exponents. Here I'm going to multiply the exponents. And for this one, I'm going to apply the exponent to the top and the bottom of the fraction. And that's what we just learned a little bit ago. So we're going to learn a couple more laws for these exponents. So looking at the first one, our first law is going to be a 0 exponent. So if I have 7 to the power of 6 over 7 to the power of 6, if I wanted to write this, using our exponent laws, like we would subtract these exponents, so I get 7 to the power of 0. Now, if I were to show this, it's like 7 times 7 times 7 times 7 times 7 times 7, 7, and same on the bottom. So if everything cancels out on the top and the bottom, remember, if everything cancels out on the top and the bottom, it just equals 1. So same thing's going to happen for this example, where I have x3 minus 3, x is equal to 0. If I were to rewrite this, x over, so when everything cancels out on the top and the bottom, all we get is 1. And what do I mean by like canceling out on the top and the bottom? It's like if I have a whole number like 2 over 2, that equals 1. Or 7 over 7 equals 1. Or if I multiplied all of these and then divided it, they're the same number on the top and the bottom, so they're going to simplify to 1. So anything with an exponent of 0 is equal to 1. Doesn't matter if it's a letter or a number. Anything to the power of 0 is going to equal 1. For a negative exponent, well, we'll see in this example, if I follow my exponent laws and I have 7 to the power of 2, and I'm subtracting 5 here, because they're division, I'm going to subtract these, I'm going to get 7 to the power of negative 3. So how could I show that, though? Well, if I wanted to show this actual 7 to the power of 2 divided by 7 to the power of 5, I would get 7 times 7 over 7 times 7 times 7 times 7 times 7, because it's to the power of 5, so I'll do it 5 times. Now if I start canceling things out here, these go away. I'm left with 1 on the top, because after things cancel, the only thing that can be left in the numerator is going to be 1. And on the denominator, 7 times 7 times 7, which is really 7 to the power of 3. So any base raised to a negative exponent is equal to the reciprocal of the base raised to the same positive exponent. So any base raised to a negative exponent is equal to the reciprocal. So if the base here is a, we get the reciprocal of the base. Remember, reciprocal just means if this is a over 1, we flip it. So it's 1 over a. And this a is still raised to the same positive exponent, but it's going to be at the bottom of the fraction. So if you want another example, if I had, let's say, 3 to the power of negative 5, this would just be equal to, again, this is over 1. The reciprocal is 1 over 3 to the power of 5, like this. So if I have a negative exponent, you just flip it into a fraction, keep the exponent on the 3 still, or on the number it's with, and it changes signs once it moves down. Alright, last one. We actually have the same idea here, where if we have any fraction base, you might see the word rational too. I'm going to put fraction because I think we all know what we mean by fraction, but rational is the proper word. Any fraction base raised to a negative exponent is equal to the reciprocal of that base raised to the same positive exponent. So here we have like a fraction base 2 to the power of negative 4 over 3 to the power of negative 4. Because this is the same on both of these, I could use my exponent law here to say that this is 2 over 3 to the power of negative 4. Because we said negative 4 can apply, if it's like this, negative 4 applies to the top and to the bottom. So now if I were to show this, I could show like the 2 to the power of negative 4. We said before, like up here, that if it's like this, I could show it like 1 over 2 to the power of 4, where I just take the reciprocal, I move to the bottom of a fraction, and I make the exponent positive. Sorry, let's make that look a bit nicer. And then I could do the same for 3 to the power of negative 4. Again, just the top numerator and denominator here, I'm just doing them separately. 1 over 3 to the power of 4. So then if I'm dividing these two, 2 over 3 to the power of negative 4, that's the same as me dividing this, divide this, so it's going to be this divided by this, which when I do division of fractions, end up flipping this and changing the sign to multiplication, and I'm left with 3 to the power of 4 and 2 to the power of 4. So notice that all it is that instead of being in negatives here, all we did was we flip the fraction and then change the signs of the exponents. So here, if the fraction is ab to the power of negative m, I can write that as b over a to the power of positive m. So if I have a negative exponent with a fraction, I just flip the fraction and then make the sign, the exponent a positive. And if I have a negative exponent with just like whole number, remember that's still over 1, any whole number, so I'm just going to flip it and then change the sign of the exponent again. So let's get to some examples. Alright, example 1, let's evaluate each of these. 12 to the power of 0. I don't even have to think, we just know as soon as it's to the power of 0, it's 1. Next one, negative 1 over 3 to the power of 0. Well, if I show my steps here and I apply this 0 to all of these, negative 1 to the power of 0 is just 1, and 3 to the power of 0 is 1, so I'm left with just 1. X to the power of 0, 1. Negative 7 to the power of 0, but it's not in the brackets, so it's actually going to be equal to 1, which is equal to negative 1. Last one, I'm multiplying these two. 2 times 0 is 0. 0 times 2 is 0. 1 plus 1 is equal to 2. So that's the first one, just working with 0 as an exponent. Remember, it's equal to 1. Our example 2 says simplify its expression as a single power with a positive exponent, and then evaluate if we can. So for the first one, we see a negative exponent. So remember, any whole number is really a fraction still over 1. So if I want to find it for a positive exponent here, I'm going to find the reciprocal. So by flipping the fraction, the exponent stays with a 3, but once I move it to the bottom of the fraction, it becomes a positive exponent. So now this just becomes 1 over 81. For question B, same idea. Negative 4 to the power of negative 3, still over 1, so I'm just going to find the reciprocal. I get 1 over negative 4 to the power of 3, which is then equal to 1 over, negative 4 to the power of 3. Negative 4 times negative 4 times negative 4 will give me negative 64. And then I have students ask me, like, what do I do with the negative? Does it stay on the bottom? Does it stay at the top? Just know that, like, remember, fractions mean division, so I'm saying 1 divided by negative 64. Even if I put it at the top, it would be negative 1 over 64. It means the same thing. So I just, you can just leave it in the middle, leave it on the top, leave it on the bottom. So for C, negative x to the power of negative 6. Same idea, I'm going to find the reciprocal, move this to the bottom of it. So we get negative x to the power of 6. And again, we're flipping it to the bottom so that this exponent becomes positive. Question D. Same idea here. I want to do the reciprocal of this. Keep in mind that 3 here doesn't change signs because either way, 2 to the power of 3 is 8, and even if I move it to the bottom here, so we're still representing 8 on the bottom. It's only the outer one that's going to change signs here. So it's going to be like this, and then if I wanted to, I could make this 1 over 2 to the power of 6, which is 1 over 64. Now you could be wondering, well, can I just do it the other way? Can I like multiply these first? And yes, you can. And you're going to find you get the exact same answer, whichever way you do it. So either way is fine. All right, last one. So if I have a fraction and I have a negative exponent, you find the reciprocal, and then once I do the reciprocal, I change the sign of the exponent to positive. So then I will apply this to both of them. 9, negative 7. I get 81 over 49. And that's my answer. Okay, last few. These are a bit trickier, but they're not too bad, I'd say. Alright, so the top ones here, I'm going to zoom in a little bit more. X to the power of 3 plus or times x to the power of 2. I'm going to add these together. I get x to the power of 5 over x to the power of 5. That is equal to x to the power of 0, which is 1. Next one. 3 to the power of 3 times 3 to the power of negative 2 over 3 to the power of 4. So again, I'm going to work with the top parts first. Same base. I'm multiplying that. I'm going to add them together. So 3 plus negative 2 is 3 to the power of 1 over 3 to the power of 4. Because 3 minus 2 is 1. Or just check on a calculator if you want to. 3 plus negative 2 is 1. And then I'm going to subtract these because I'm dividing. I'm left with 3 to the power of negative 3. But we don't really want a negative exponent, so I'm going to find the reciprocal, keep that at the bottom, and make it a positive exponent. And we'll simplify this again to 1 over 27. All right. So hopefully I didn't go too fast there. We just did the top part, got this, subtracted them, and then we just did our negative exponent stuff here. All right, for C, a couple things I can do here. I see a negative exponent here. I could just first find the reciprocal. X to the power of negative 5. And here we have it where it's x to the power of negative 5 over x to the power of negative 5. These actually cancel out. Because they're saying that they have to be the same number. Let's say if x is equal to 1, 1 to the power of negative 5 over 1 to the power of negative 5, they're going to cancel out either way. So after I do this, these cancel out to equal 1. I'm left with just 3 over 2. Okay, our last one here. There's a couple ways we could do this. One way, if we wanted to, is first just apply this to make it a positive exponent. And then I could do my exponent here apply to the top and the bottom of this fraction. So I get 1 to the power of 3 over 2 to the power of 3. 1 to the power of 3 is just 1. So I'm left with 2 over 2 to the power of 3, because these have the same denominator, so I'm just going to add the numerator because I'm adding fractions here. And then if I wanted to, I could just, this is going to equal 2 to the power of, sorry, 2 over 8, which is equal to 1 over 4. So that's one way you could do it. And I say that's probably the easiest way. You could also, like, if we had it over here, sorry, I'm just going to, it actually just kind of does this step again, where if we have 1 over 2 to the power of 3 plus, 1 over 2 to the power of 3, we add these together, this is the same as 2 over 2 to the power of 3. We can think of this as being an exponent of 1, and then I could subtract these to get 2 to the power of negative 2, which would then simplify to give me 1 over 2 to the power of 2, which is 1 over 4. So those are the different ways we could do this. Either way is fine, as long as we get to the right answer. So here's your homework. This is 2 sections, because again, I think they're pretty quick, and thanks for your time.